All right, so we're going to dive into 2.3 now, which is essentially other displays of data. Now, some of these questions, because of the relationship I have with your textbook, I'm just going to kind of help you out with. So, first, they say, why is a dot plot not very effective for this data? And, well, let's look at what a dot plot is. First, whoops, these two, oh, there we go. First, these two are not the same data, just to say that these are just the two that we're going to look at here. I want to show you what a dot plot is. Number one, a dot plot should kind of remind you of a histogram, if you think about that. It's just there's going to be a dot for each one of those numerical values. So here's one data value is 4, two data values are 5, four data values are 6, so on and so forth. And so if I look at this data and I think about the number line, um, number one, I don't really see any of these data values repeat at all. And number two, they're pretty spread out. So, why would a dot plot not be effective? Because maybe another way of saying that is the data set is too small to reveal important characteristics. Essentially, there would just be a flat line of one data point each time unless we decided to bin them in some way. So, that'd be our answer for number one. There's just not enough data to really see a nice trend. Which of the following would be more effective? And this is where I'm going to just let you know. We have shark attacks over the last several years. We don't know what years those are, but it would actually be nice to know those years, and the answer would be a time series graph. I'm going to tell you that answer because never did we cover that anywhere else. I don't like this question, but there we go. It's still important to know that just because you have data doesn't mean you need to put it in a dot plot or a certain shape. Sometimes your data just isn't good in a display and there's something else you should do with it, but again, we don't talk about time series in this class. Up next, you have these data values and they want you to form a dot plot. And so again, what I want you to notice is, well, now your data is, maybe not clustered close together, so to speak. There is a 50 here and some 60s and 70s and 80s, but what I want to show you is even within that range, right, there's some repeatability and some heights to some bars we could get, so to speak, from this. And so how do we figure out which one this is? Well, first, I'm kind of noticing again that data point of 50. There's only one of them. And first, well, that's not even on 50. This is on 50. And C and D are. Next, let's look at the peaks of C and D. C's peak is at 70. There's about 4 or 5 values there. And D's peak is at 80. So which one had 4 or 5 values? Was it 70 or 80? It looks like 70. I see that about 1, 2, 3, 4, 5 times. So my data value must be C. So really, you're going to learn to be a good, process of eliminationer in this class when it comes to these multiple choice questions. Are there any outliers? Now this time, we kind of talked about it before, an outlier or an unusual point would be something that's far away from the rest of the data. It's not connected, so to speak. And so that point of 50, you can see there's a bin here, so to speak, and a bin here that didn't have any data. We had 2 bins of no data, and then one showed up very low. So I would consider that one, yes, to be an outlier because it's far away. And we'll go from just kind of guessing to being precise about that. Now, up next, we have a stem and leaf plot. Stem and leaf plots are often misunderstood, but let's do this. I think this will clear it up. If we look at this stem and leaf plot I have as an example, the data values would be 41, 52, 57, 58. I want to get to the point of 55, 66, and then here we go, 70, 75, and look at this, 78, 78, 78. You can see that's where the duplication comes in. And so, 95. So that's all a stem and leaf plot is really, if you want to think about it this way, in this case, it's breaking the tens place from the ones place, but you can stitch them back together, right? 40 and 1 is 41, 50 and 2 is 52, 50 and 7 is 57. So there's some space, so to speak, almost like a dot plot, right? Those spaces are equally spaced every time, so we can start to see some heights and some, peaks, and maybe a right and left side is it symmetric or not. There's still a way of doing that with a stem and leaf plot, but now what we're getting is we're getting a condensed way of writing 78 three times. It's just 7 on the stem and then 3 eighths. But notice it's going from least to greatest order. It's still ordered. So 41, then 52, then 57, then 58, and so on and so forth. And so for this one, they want you to construct the stem and leaf plot. Now, what we can do for this one, just to, again, help you as you make your stem and leaf plot, let's show you this. I would open this up in StatCrunch, and one thing you're going to learn how to do in this class is be a good organizer of your windows. Now, you can actually make a stem and leaf plot directly. All right. But beyond that, I think really all you need to do is, and I'll trust you can work out how to do that. Let's see here. Leaf unit probably is going to be the tens place. Compute. Whoops, maybe it's not the tens place. Maybe it's the ones place. Oh, the leaf unit. Sorry, I was thinking stem unit. There we go. All right, so that looks like my stem and leaf plot there. Now, that would help. And so one thing also to know is that the way you type this is it would be, you'd have your 6, and then you would have your 0, 0, 2, and then 4 4s. And you're just going to type it like that. No spaces, no commas. You're just going to type the 6 and then each one of those leaves. Now, really, what I think would be a better exercise for you is really just to say, hey, let me take my data and let me sort it. And since there's only one column, I could just select all in ascending. Whoops. Select var 1 by ascending. And at this point, really, I still have my stem and leaf plot here. I just have to do a little bit more thinking, but I can see my 0, 0, 2, 4, 4, 4, 4. So, again, when we were in elementary school and we were making these kind of plots, our first step was always to reorder the data from least to greatest. But you can go ahead and press data. You can sort. And again, what I missed the first time is I missed, oh my gosh, sorry, the fact that you have to at least select one column and then sort by it. But after that, again, that's pretty nice that then you could make your stem and leaf plot and so on and so forth. But I'll leave that to you. You can see the next one would be 7, 8, 9. You could also see that, again, you had the stem and leaf option there, so that was nice as well. All right. Up next, just to let you know, and this is where we'll kind of skim over things a little bit quickly. Oops. Give me a second here. My pages got out of order. Where's that side menu? Whatever, I'll find it later. All right. We'll just say other displays, and we'll just make a note here. Pareto, I think that's how you spell it. Pareto, yep. Charts take categorical data and order them from most frequent, or in other words, highest bar, to least frequent, which would of course be the lowest bar. And we'll go ahead and give you this note as well. Charts with heights and bars are preferred over pie charts. Again, don't ask me why. That's your book's opinion, and I don't necessarily agree. So, which one's the Pareto chart? Which one goes from highest peak to lowest peak? Well, first it goes E is the highest, so there's E with the highest. This one has H as the highest, and H only had 60, so it's definitely A. All right. And then, let's see here. If someone was wanting to get a job, what would be the most effective approach? Well, evidently, let's see here. How did people get jobs? It says, how did people get jobs? Executive search firms had the highest frequency, so evidently you should go with executive search firms. It gives you a quick way of seeing what the most frequent item was. Now, here's this question about saying, hey, take a Pareto chart and then make it a pie chart. Just watch out for that second part. We prefer bar charts over pie charts statistically, just so you know. Now, last but not least, let's talk about this real quick. We'll just put a few lines here and we'll let you figure out what that means. So, bad graphs. Graphs that try to distort data by either one, we'll say, let's see here. How do I want to phrase this? Adjusting the window to not, or to exaggerate differences in heights. And also we'll say graphs that use 3D objects. All right, so those are going to be your main bad graphs. Now let's talk about the first one. This graph has a what I would call zoomed in window. And why would I say that? Because it's not starting from 0. And so if you were to just look at these heights, and I think that's what we're trying to say here, is, let's see here, it creates the impression that men have salaries that are more than twice the salaries of women. Well, I think what they mean by that is if you look at the height of this bar, it's more than twice the height of the women bar. And so that does sound right. And there we go. So the issue is that this graph is zoomed in. It's not starting from 0 and going up to 80,000. It's starting from 50,000 to, again, just show the difference in those two peaks without showing the wider graph. And so, no, because it doesn't start at 0. And so what would be the correct data display is the next question. And, well, let's see here. A little bit below 60,000 and a little bit under 80,000, it looks like this graph. So, number one, is there discrepancy? Yes, right? Is there still some valid statistics we could show and prove that, yes, there is, as we call it today, the gender pay gap, does that exist? We could definitely prove that through data, but, again, displaying a chart like this, again, can be a little bit, sensational, right? It shows a really, really big difference. There is a difference. I mean, we would still consider this statistically significant, trust me, but it's not a true image in this case to kind of distort it and start from, well, the women's chart is barely anywhere and the men's chart is fully, up to about 80,000 or up to the height of the graph. All right. Well, look at that. We just saw a 3D object, so there you go. Let's look now at 2.4. All right, 2.4 is going to take a little bit more to explain. Even though there's fewer questions, it's a little bit of a headier topic. We're going to talk about scatter plots and correlation. So, first thing we need to say in bold is correlation does not imply causation. All right, so just because two things appear to be correlated doesn't mean one of them causes the other or vice versa. There can be things that influence one another, but that doesn't mean they cause one another. Or there could be things that look like they influence one another and they actually don't at all. They're just related by some other variable that we are unaware of. And this course isn't going to be totally concerned with that, but you just need to be made aware of that. Let's see here, who was it? My 11th grade chemistry teacher taught me this for some reason. Or it was the first one where it stuck in my head, and he talked about, ice cream sales and shark attacks. So the more ice cream you sell, the more shark attacks there will be. But of course, the problem there is we're just not considering the fact that maybe it's summertime, and so people are hot outside, so they want a cold treat. And also it's hot outside, so sharks are going to be, in the warmer waters near the shore. And so ice cream sales are definitely not bringing the sharks in, but it's the hotter temperatures, right? So you have to be careful about saying just because two things are related, does that mean I know one causes the other? Maybe not. Maybe there's an underlying factor that we don't know of yet. Now from there, let's talk about R. Define that early on, since your homework's question 1 did that. It's the correlation coefficient. Now we have to be careful with our wording here. It's, let's hear. It measures the strength of a, we'll put it in bold, linear relationship between two quantitative, we talked about that a little bit, but quantitative versus categorical all right, and so there we go. It measures the strength of the linear relationship between two quantitative variables. Also, one thing we should know is R, just to say early on, should be, we'll make it lowercase to match the homework. R should only be, let's see here, confirmed by looking at a scatter plot. And we'll put in parentheses here, it could be that R is showing a strong relationship, but the data is not linear. So, in other words, R is the way we calculate it, and the good news is we're not going to do it by hand because it's honestly a nightmare of a process, but the way you calculate this relationship between two variables, well, just due to the math of it, you could get some strong looking relationships out of R, but it might not be that you actually have a strong linear relationship, right? We need to look and make sure it's linear when we then look at the measurement of R. Okay, let's see how far that took us so far. We use R to denote the linear correlation coefficient. Why do we refer to it as being linear? Because the term linear refers to a straight line, and R measures how well a scatter plot fits a straight line pattern. Great, that sounds good. So the first one was right in that case. But again, that's what R is there to measure. It's how close do I fit a line. So maybe let's write it this way, a little bit non-mathy. R measures, how, we'll say tightly, the points of a scatter plot could conform to a, we'll say, special line which passes through all the data. All right, we'll talk about that special line in a second. There's a name for it. It's actually usually called a regression line or a least squares line, or a line of best fit. Least square regression line or a line of best fit. But for right now, again, we're not there yet. We'll just call it a special line. Okay, if we find a linear correlation coefficient, does that indicate, between carbon dioxide and atmosphere temperature, does that indicate that one causes the other? Now this one is honestly pretty loaded, because maybe this is dicey, but I think in today's modern age, I think we do know that carbon dioxide has some effect on the atmosphere. Hopefully that's not too spicy of a statement. But at the same time, just because we notice that can't mean that we have confirmed that it causes. We can say there's a relationship, but we don't know if it causes it. We have to do another study. So, no, the presence of a correlation does not imply causation. So there it was. They just used a little bit more flowery words around it. Okay. What is a scatter plot and how does it help us? Well, that's a good question because we haven't seen them yet. Let's maybe skip this question and then go back. So here are some scatter plots of some data. Now this first one is a little bit silly, but it's the height of the president versus the height of their opponent. So, maybe someone early on in history just thought, hey, Abe Lincoln's tall. Maybe that's why he was elected president and the other person wasn't. So maybe that's when they decided to say, well, let's study all their heights and see if people just like taller people over shorter people. And so they've recorded some presidents' heights and their opponents' heights, and they wanted to make a scatter plot. Well, hey, look at that. We have the data. We can also click open in StatCrunch once again. And we could actually say stat, and we could say that I want, a graph, and I want a, where is it? Scatter plot. My x variable, what is my x variable? Let's look at all my graphs. They had precedence height on the bottom, precedence height, precedence height, precedence height. The horizontal axis is the x-axis, so that would be precedent, y variable's opponent, and let's just go ahead and compute that. Now this looks pretty messy, but that at least means I can now look at this and look back at my things right here. It's definitely not C or D, because it was, again, pretty messy. It's definitely A or B. And again, we want to do some good process of elimination. So what I'm noticing between these two is, take a look, this one has kind of 4 up top and 2 on the bottom on this kind of upper right corner. This one has 2 on top and 4 on the bottom. So let's look now. I see 2 on top, 4 on the bottom. It must be this one. Just notice the scaling is going to be different, so it kind of throws you off when you first look at them. They don't quite look the same, but they are. And maybe you could choose some options here that then scale it, or maybe you could even, zoom in until it looks similar, right? So you could use all those tools. Does it appear that there's a correlation? I would say no. It doesn't look like I could draw a straight line through this. It kind of almost looks like a circle almost. It looks like anywhere I would try to fit a line would be almost symmetric between it, and that's not what we want. All right. So up next, let's look at scatter plots and R. So before we look more at the homework, because some of those will be a little confusing, let's just go ahead and draw some scatter plots and then make some conclusions here. So here we have XY axis, so we have another XY axis, and here we have another XY axis. And you know what? I'm going to pause this so you don't have to see me draw all this, if I can. All right. So before we continue, I just wanted to kind of talk about, again, what scatter plots are and what a line of best fit is, or a regression line is. And so let's see here. I can draw some shapes here. So a line of best fit in this case, this would about be your line of best fit. You can kind of see I'm somewhat guesstimating, but you can just kind of see that, again, this pretty much fits right in between the points. There's about the same amount of points above as there are below. For the next one, if I were to draw a line, hopefully you would agree that the line of best fit would probably be somewhere over here. Maybe a little bit more like this. But again, we use computers to figure this out. You don't need to worry about guesstimating that on your own. Now this last one, let's see here. We'll go somewhere around here. All right, I think. And so what I want you to notice is that we're always trying to essentially have the line travel as close as it can to all the points when possible. And so one thing just to say, to talk about maybe symmetry is, right, if I draw this line like this, it is still, cutting the points above and the points below pretty well. But this, making it more vertical, is definitely a better fit for the data, because now it's in a way closer to all the points. And one thing we need to also note is that the closeness of points is always measured vertically. This one took me honestly a long time to grasp, and I wish it was kind of more spelled out for me, so I'm going to spell it out for you. When we talk about points being close together, we don't just draw random lines. We always draw vertical lines, all right, directly to the line. And so some of them will be higher than others, like this one here is way off if you think about it, right? But even so, some of them are still pretty close, and these are technically better than, again, if I were to flip that around and take this line again and put it this way, Now all of them are going to have really, really high vertical points away from the line. So the best fit really would still be to cut through like this in some way, shape, or form, because now a lot more of your points are still going to be actually fairly close to your line than they would otherwise be. But it's always measured vertically, but really you can almost tell visually. It's like, where does a line best pass through the middle of my data and still follow the general trend of the data. Now, here's the next thing I want to say, or the next note that's important to know before we continue, is R measures the closeness. Again, well, actually, we already measured it, so do I need to write that again? R measures how tightly the point of a scatter plot could conform to a special line. You know what? Maybe we have to put it here in the top section. Last thing is R takes on values, or in other words, you're only going to get a value between -1 and 1. So from there we could say the closer to -1, the more tightly the points fit to a negatively sloped line. The closer to 1, the more tightly the points fit to a positively sloped line. Goodness. And we'll say the closer to 0, the harder it is to see where the line should be at all, right? So if you're close to 0, then maybe there isn't a linear relationship at all, or you shouldn't be trying to fit a line through your data. I know that's a lot there and a lot of writing, but let's look at these examples. And what I want to point out here is that if we were to guesstimate, and again, there are calculators to do that, and we'll look at it in the homework, what R would be, I would think R in this case would be probably about, 0.86. There's definitely a positive trend here, positive slope, right? As I move to the right, I go up. And the points are pretty close. But then when I look at maybe this next example, look at how tightly these points are to the line, but there's a negative slope, so this would be R equals maybe, 0.93, something like that. Because this is a very, very tightly, the points are very tightly wrapped around where this special invisible line would be. And there's a negative slope. Now, last but not least, here's what I want to mention here, and here's why I'm writing out all those extra notes, is take a look at this one. Your slope is positive and the slope is steeper, but does that mean that R should be greater than 0.86 like this one was? The answer is no, and maybe you caught it from my tone that I was warning you of that. R in this case would probably be something like 0.64 because, I'll say this, even though the slope is steeper, R only cares about the tightness or trend of the line, right? It doesn't care about the steepness of the slope. This R is weaker than this R because these were more tightly fitting around the line of best fit. These are more spread out. There's more space between the line and the actual data points, so your R is going to be inherently weaker. I still see a positive relationship. It's a steeper slope, but the points are not as tightly fitting around as over here, so a weaker positive value of R, because the R are positive for the first and the third because the slope is positive. I don't care about how steep it is. I care about the tightness of fit to the line of best fit. All right, and here again the R is negative, and it's very close to -1 because those are very close to being tightly wrapped around that line of best fit. Hopefully that clears that up. And once again, we can look at some examples here and open them up in StatCrunch. And honestly, you're going to go right to scatterplot. Your X will be probably the tar, and your Y will be the CO, and we'll confirm that by looking at the graphs. Let's see here. It says use use tar for the horizontal scale, carbon dioxide for the vertical scale. So there we go. Tar for X, CO for Y. That's a pretty tight positive relationship. And again, just to kind of get my right answer, I see 1 or 2, 1 or 2, and then 1 up top and 3 below. So let's see which one that is. 1 or 2, 1 or 2, 1 up top, 3 below. It looks like it's B. And does there appear to be a relationship? I would say yes, and it's as the amount of tar increases, the carbon dioxide also increases, right? There's a positive trend. So as one moves to the right, the other moves up. Both are increasing, right? From 0 to 20 is an increase, from 0 to 20 is an increase. So as you go right, you also go up. As you increase, you also increase. Awesome. All right, up next. This is where we kind of, I want to say we're jumping the gun a little bit, but it's also not too bad to introduce these ideas early. So this is less to do with correlation and more to do with where we're going to end up with in this course in general. So critical values and significance. So what we're going to look at, and especially in chapter 3, is we're going to look at this idea of lower fences and upper fences. So what we're going to do in general is we're going to say if data's, let's say, what do I want to say? Like this is a correlation coefficient. We could almost refer to that as a statistic. So we'll say if data's summary statistics fall within lower, and we'll put this in bold, expected lower and upper fences, then the data does not, we'll put that in bold and caps, show a significant result. Significant, I can spell. And guess what? The opposite's true. So if data's summary statistics fall outside of expected lower and upper fences, again, that's some interesting wording. Whoops, that was a random paste. Oh my. Then the data, oh my gosh, does show a significant result. Okay, so based on that, I think the only other thing to say is critical values are considered lower and upper fences. Great. So let's see what on earth I mean by that. So it says for a data set of brain volumes and IQ scores of 8 males, a correlation coefficient is found to be 0.423. Now, if you're thinking about that so far, here's what you should be thinking. It means if you were to draw a line through the points, your line of best fit or your regression line would be positively sloped, but your points would be pretty scattered around it. And I'll also even say this, if you were to actually probably look at the scatter plot, and maybe we'll do that. Actually, we don't have the raw data values here, but to the human eye, honestly, 0.423, we wouldn't even be able to see a discernible trend. We would probably say, oh, I don't think there is a correlation at all. The computer will show you one because it can calculate your correlation coefficient perfectly, but you and I probably wouldn't even discern it as being linear at all. Now, from there, it says, okay, we have a correlation coefficient of 0.423. It's looking somewhat positive. Now, but also, there's only 8 males here, so that's not a lot of data to go off of. So even though there's not a lot of data, because I'm showing some positive trend here, is that enough to conclude that maybe brain volume and IQ scores are correlated somehow? Well, that's where we then open up this chart. Whoops. Oh my. So let's look at this example in specific. There's my critical values of R, and I think I'll even go ahead and copy some of this wording here. And based on that, we'll be able to draw a picture. Okay, so we have our 8 males, and they show a correlation coefficient of 0.423, and essentially, is that enough to conclude there's a correlation coefficient? Now, from there, let's look at our highlighter. For 8 males, for 8 pairs of data, 0.707 is the critical value. Here's one thing we need to learn. Since R could be negative or positive, the lower and upper fence for 8 pairs of data would be, and we can draw this out. We have a spectrum here. Actually, I don't even need arrows. It goes from -1 to +1. And according to this chart here, maybe I should use yellow, although I don't want to use yellow because it's not easy to see. Here's negative 0.707. Bear with my mouse pad writing. Here's positive 0.707. And so here's the idea. Here's your lower fence. Here's your upper fence. Your upper fence. And also, by the way, here's 0 in the middle, just for some context, right? Because R could be anywhere from -1 to +1. And so our wording, again, like we said before here, is, if I am within my lower and upper fences, then I'm not significant. If I break out of the fences, then that is significant. Simple ways of saying it is, if your animals are inside of your fence, then that's not scary. But if your animals are outside of your fence, you better go get them, right? It's significant if you jump outside of the fences, if you go beyond the boundaries of what we thought would be expected. And so where does my data value sit then? My data value, or our data value for this example, sits right here at 0.423. So, gosh, that's a lot of explaining, but hopefully you knew the answer a long time ago. Since 0.423 is within the lower and upper fences of negative 0.707 and positive 0.707, the result is not significant, which means, another way of saying that is, there does not appear to be a correlation between brain mass and IQ. Great. And we just answered it. All right, so because we were within the fence, we do not have a significant result. If I don't have a significant result, then that means I can't conclude there's a correlation. So let's see here. Significance means a correlation is observed. Maybe that's one last thing to say, right? If you are significant, then there does appear to be a correlation. If I'm not significant, then there does not appear to be a correlation between those data points. So, same thing here. We just go through the question. We write down the critical values. Now, the thing you need to realize is, again, the negative version exists even though the table just has the positive value. Mathematicians are lazy. Mathematicians understand that R could be a negative or a positive, so they just need to write one table and they know that it counts for both. But we need to write both of them out actually. And so because it's between the critical values, there is not evidence to support correlation. Whew, goodness. All right. Up next, we learn the same thing, but we learn about p-values. So here we go. Another early one. And honestly, I know we spelled all this out, but it's really important to get this idea early. It's going to show up in a lot of other chapters. It's kind of Again, jumping the gun a little bit and explaining it so early, but never hurts. So now let's look at p-values and significance. Now, this is going to take a lot, but here we go. What is a p-value? It is the probability of getting your random sample result if the data was assumed to have no significance. Now, there's a lot to say here, but what we're going to say early on is if our p-value is low, and we'll say 5% or less. All right. Now, in other words, we're looking at 0.05. Then we don't think we got lucky. We think our assumption was wrong, and there is significance. Goodness. That's a lot to take in. This statement will really, I will tell you this, it drives the entirety of Chapter 8 and Chapter 9, the end of our course. So maybe that's why they bring it up so early, just to get it somewhat in the back of your head. But again, maybe let's hear the idea here is, well, let's look at the question as we go through it. So this is saying, all right, same idea. We have brain volumes and IQ scores of males. And we got a p-value of 65.2%. Now, the question is, what does it mean to have no significance? Well, no significance means I don't think that they're correlated at all. And so I got by chance a result that would happen about 65% of the time if it wasn't correlated. Right? If you can read that right, 0.65 translates to about 65%. So, the assumption is, for a p-value, not based on the wording, but just in general, the assumption is there's no significance. And based on that assumption, the data I got would happen about 65% of the time. Now, that's not that rare, right? So we should say, or rare. So in other words, if our p-value is low or rare, then we do think there is significance. But the opposite is true. If my p-value is high or above 5%, then we do think, maybe not we got lucky, but we do think we got a expected result, and we don't think that it's significant. So we got at least extreme as 65.2%, which is high. That happens more than the majority of the time. In other words, high, your baseline should be 5%. It's way more than 5%. So it's not sufficient to say there's a correlation. All right. So catch that wording. Let me go back real quick. Whoops. Oh, no. All right. Sorry. Different numbers, but same idea. That is a high probability, so there's not significance. Whoops. And we had over here that if it's a low probability, there is significance. So just notice how that negates. And it looks like the other example is probably going to be similar, but really early on, to close off Chapter 2, we talk about two big ideas. We talk about critical values and p-values. And there's just one more thing to say, and it's this. Critical values and p-values will, we'll say, always agree. They are two different ways of answering the same question. The question being, is there significance? And so what we'll do through probably the courses of like chapters 7, 8, and 9 is we'll learn that, yeah, critical values are just another way of thinking about p-values, and p-values are another way of looking at critical values. Your upper and lower fences will translate to probabilities of likelihood, And if you are shooting for a target level of 5% likelihood, you can translate that back to a critical value. There's a one-to-one translation between these two. You just haven't learned what those formulas are. It's kind of like saying I could figure out how hot it is in Celsius or Fahrenheit. They're two different numbers, but they will translate to the same temperature I feel when I walk outside. Same idea in statistics. I can find something significant or not based on a critical value or a p-value. The way I think about them is different, but ultimately they translate to the same result every time. So that's a lot to end chapter 2 on. It kind of feels out of nowhere, but we'll continue on with chapter 3 in the next video.